Good morning, good afternoon, good evening. Let's solve some differential equations problems. And from our text, these problems are on page 111, and they have to do with linear second-order differential equations. Now, here's the first problem we're going to look at today. It's problem 4, page 111. And it's y double prime plus 25y equals 0. And we look at that and we see it's ordinary, it's second order, it's linear. Now it's ordinary because there are no partials. It's second order because the highest derivative is y double prime. It's linear because it's linear in y and the derivatives of y. So it's a second order linear ordinary differential equation. And we're given two functions, y1 and y2, and asked to verify that they're both solutions. And I've done that for you. And how would you do it? Well, you would take the derivatives and substitute them in the original equation and see if they work. But I've done that for you. So they are solutions, and I've also determined that they are linearly independent. So if they're linearly independent solutions of the homogeneous differential equation, Theorem 4 says that a linear combination of y1 and y2 will be a general solution. So almost just by writing it down, we found a general solution to the original differential equation. Now, the problem 4 asks us then to find a particular solution that satisfies the initial conditions y of 0 is equal to 10 and y prime 0 is equal to negative 10. So find a particular solution is just to say find C1 and C2, those are what were the arbitrary constants in the general solution. Find particular values for C1 and 2 so that the initial conditions hold. So we ought to be able to do that. Let's write down what y would look like if we substituted the initial conditions here. So I would have 10 is equal to C1 cosine 5 times 0 plus C2 sine 5 times 0. So that would be substituting in y of 0 equals 10. Now we also know that y prime of 0 is negative 10. So negative 10 would be equal to, now I'm going to take the derivative of this as I write it, so pay attention that I don't make a mistake here. This is going to be negative 5 C1 sine, see, I almost made a mistake, sine 5x, only we'd be evaluating at x equals 0, so 5 times 0, and then let's see, here's our y, so I'd be taking the derivative of sine and using the chain rule, so the derivative of sine would be positive cosine, so this would be 5 C2 cosine 5x, but then we'd want to evaluate it at x equals 0 using the second of the two initial conditions. So these would be simultaneous equations. Now let's rewrite these, and if I rewrite, I get 10 is equal to, well, 5 times 0 would be 0, and the cosine of 0 is 1, so this would be a C1, and 5 times 0 is 0, but the sine of 0 is 0, so this term disappears, and the first equation evaluates to 10 is equal to C1. And the second equation evaluates to negative 10 is equal to, and the sine of 0 would be 0, so this term drops out. And then I would have a 5C2, and 5 times 0 is 0, but the cosine of 0 is 1, so this would be 5C2, simultaneous equations. And from these, I get that C1 is equal to 10, and down here I don't even have to substitute, but C2 would be negative 10 divided by 5. C2 would be negative 2. So the particular solution would be y is equal to 10 cosine 5x minus 2 sine 5x. And certainly you could verify that that is the particular solution we seek, but in fact it is. All right, so there is problem 4. Now let's jump down to problem number 21. And 21 says, are these linearly independent? And the functions they're asking about are f of x equals x cubed, and g of x equals x squared absolute x. And the answer is no, they're not. And the proof would be, suppose they are linearly dependent. I'm sorry, I got that wrong. The answer is yes, they are linearly independent. Suppose that they were not. Suppose they were linearly dependent. Then it doesn't matter. We can say here, it doesn't matter. We can say then f of x is a constant multiple of g of x, and although I didn't say it earlier, I think the text says on the real numbers on R. So we're supposing that they're linearly dependent. A consequence of that supposition is that f is a constant multiple of g, that is x cubed is equal to k times x squared times absolute x, which would be x is equal to k absolute x on the real number line. But this would imply if x is greater than 0, then k would have to be 1, and if x is less than 0, then this would be a negative number, and this would be a positive number unless k was less than 0. So if x is less than 0, then k would have to be negative 1. But there is no such k. So sometimes we use that symbol for a contradiction, and when you reach a contradiction with your supposition, then we're going to conclude that this supposition was wrong. They're not linearly dependent, they have to be linearly independent, so we'll stand by our answer yes. So that was an easy one. And number 4, let's see. I guess this was just to solve this equation. 9y double prime minus 12y prime plus 4y equals 0. So as always, when we're solving differential equations, we look at the equation and we try to decide what kind of a differential equation it is. And so I guess the most obvious thing would be ordinary. And then second order would be another fairly obvious thing. And then look at it, scrutinize it. Linear would be another obvious thing. And constant coefficients. So if we have this sort of differential equation, we know that we would find the characteristic polynomial, and the characteristic polynomial would be 9r squared minus 12r plus 4 equals 0, and then we would look for zeros of this characteristic polynomial. And of course, it's not necessary that you factor the characteristic polynomial, but very often that's going to be the easiest way to find zeros. And so I look at this, and maybe a little trial and error, I come up with 3r minus 2, 3r minus 2 equals 0 by factoring this. And then reading the factors, I see I've got repeated real roots or zeros. It's really zeros. Roots and zeros are used interchangeably here, but it's really zeros that I'm thinking about. Repeated real zeros, and that would be r equal to 2/3. So r equal 2/3 would be a repeated 0. Now, I don't remember which theorem number or result number it is, but if r1 is a repeated 0, then a general solution is, I guess since I started this way, I'm going to call it C1 e to the r1x plus C2 x e to the r1x. Now you see the exponential repeats, e to the r1x, e to the r1x, if r1 is a repeated root, but I add an x to this second solution, and that makes these linearly independent solutions, and their sum will be a general solution for the starting, right here, the starting differential equation. So in this case, we'd be talking about y is equal to C1 e to the 2/3 x plus C2 x e to the 2/3 x. So there's your general solution. So that was pretty easy, wasn't it? And that was problem not number 4, but problem 40 out of the page. 111 set. So that's enough for right now. We're going to move on to the next section, which is going to be on nth order linear differential equations with constant coefficients. And we'll see how what we've learned in this chapter and section transfers over to the more general material. So thank you for being here, and have a good rest of your day.